use an infinite number of cells. You can use 100 cells, 1,000 cells, 10,000 cells, maybe even 100,000 cells if you're willing to wait long enough. But you can't use an infinite number of cells. So for 100 cells, you might get a curve that looked like that. Where's the MMP? No telling. For 1,000 cells, you might get a curve that looks like that. Still hard to tell. The best thing you can do with a system like this is that you go to as many cells as you can afford to wait for, and then you take the results and you do some sort of extrapolation to give you a predicted number of a predicted curve for an infinite number of cells. And if you do that, you can usually narrow the range of the possible solution to a reasonably narrow level. You can say, well, my MMP is probably somewhere within this range. But there's still that little bit of uncertainty because you're extrapolating the results. And this becomes difficult to deal with if, say, somebody asks you, well, I can't afford to run your simulator every time I want an MMP. Give me a correlation. Give me a simple correlation so that, if I change my solvent composition, I can immediately tell what the MMP is. Well, the way to generate a correlation is to generate a lot of results like this, and then you curve fit the results. Well, if there's uncertainty in each point, then you try to curve fit your results, and the uncertainties are going to make your correlation unreliable. So you'd like to minimize these uncertainties, and unfortunately it's difficult to do that with slim tube simulations. And they're still quite time consuming. And if it takes the engineer a lot of time to calculate each point and plot this all up and eyeball it and just to get one point, that's expensive. So the next technique is to do single cell calculations. Now, basically the idea behind these single cell calculations is you assume you have a pseudo-ternary type system, and you have your oil here and you have your injection gas here, and you inject some oil into the gas, let it equilibrate, you get a new gas here, and you inject some more of that oil into this gas, let it equilibrate, inject this into the new gas, and so forth, until you either get stuck on a tie line for this gas, for this oil, or until you reach a condition of line of sight miscibility for this oil. So you'd say that this oil is miscible and this oil is immiscible. And that's a relatively fast and cheap and inexpensive calculation to make. And it's perfectly accurate for vaporizing gas drive cases. The problem is that it always overpredicts the minimum miscibility requirements if you have the more typical condensing vaporizing mechanism. Because in this kind of system, in order to develop miscibility like that between this injection gas and this oil, you basically have to pressure up until this whole phase envelope shrinks out of the way of the of this path between the two. So you can overpredict the MMP by a lot sometimes with this technique. Again, if you know for sure that you've got a vaporizing case, then you can use this, like you could use the rising bubble experiments. But you shouldn't use this if you have no idea what your mechanism is, or if you know that you are likely to have a mixed mechanism. Okay? Now the method of characteristics. There are two categories of this. There's the rigorous method, where you actually solve a system of partial differential equations all the way along this path, to find that path exactly to the degree of the uncertainty that you have to discretize that path, because you solve a partial differential equation numerically, you're always going to have some uncertainties, some numerical uncertainties. But basically the idea is to solve for the entire composition path as a function of distance divided by time. Distance along the slim tube. What you're trying to do is model basically a slim tube displacement, and you find the compositions as a function of x divided by time, distance over time. Now there's been an approximate method that has been proposed by Wang and Orr at Stanford, and they say that if you assume that all the transitions from one tie line to the next are shocks, in other words, sudden transitions, then all you have to do is search for the tie lines that satisfy those shock conditions. Now in this case over here, there are 1, 2, 3 tie lines of interest. There's the tie line that passes through the original injection gas. There's the tie line that passes through the original oil, and then there's this tie line that they call the crossover tie line, where the two compositional paths intersect. The two halves of the compositional path intersect. Now that's, for a 4-component system, you've got those 3 tie lines. If you have a 10-component system, you have 9 tie lines. If you have a 20-component system, you've got 19. If you have a real oil with 1,000 components, you've got 999 tie lines. But most of the time, you describe your oil by 10 to 15 components. So you've got on the order of 9 to 14 tie lines to find. And if you assume that the transitions are all shocks, in other words, if there's just an immediate jump from the injection gas to this point, and then the composition stays there for a distance and then immediately jumps to that point, and then stays there for a while and immediately jumps to this point here, and then it stays there a while and immediately jumps to that point. Then the tie lines that satisfy those shock conditions have to be in the same plane from one to the next, so that this tie line and this tie line would have to fall in the same plane. In other words, they would have to intersect someplace outside of the diagram. And this tie line would have to be in the same plane as this tie line. In other words, those also intersect someplace. Now, if you can find those shocks, or those tie lines, and if your system does satisfy this shock condition, then you're done. You've found all the tie lines of interest, and you can see, are any of those tie lines approaching a critical tie line as you increase the pressure. So that's the way the approximate method works. Okay, so next, now we'll go back to the rigorous one for a second. The advantage there is it yields the true solution. the true dispersion-free numerical solution. Subject to the uncertainties in your fluid model, your equation of state model, of course, but let's assume that the equation of state is as good as we get, and so that would give you the true solution. But it has disadvantages. It requires solving a set of eigenvalue problems at every discrete step along the composition path. And the discretization itself could introduce numerical errors. You don't know how many discrete steps it's going to take to approximate this path. And of course, at each step, at each point, you've got to solve this system of eigenvalue problems. That makes it kind of numerically difficult and time-consuming. It can chew up a lot of computer time. It also falls apart near miscibility, because when one of the tie lines along this composition path goes to zero length, these eigenvalue problems become ill-posed, singular, more or less. And so the numerical uncertainties go way, way up the closer you get to miscibility. So it's rarely been done anywhere near miscibility. I don't think even the guys at Stanford have published a case where they show the entire composition path anywhere near miscibility. They show it for immiscible systems, and they say, well, you know, you'd extend this technique at higher pressures until you reach miscibility, but they've never done it because I don't think their algorithms are rigorous enough to solve the whole problem near miscibility. Okay? So that leaves us with the approximate method of characteristics. Now, it's theoretically appealing because if all the assumptions hold true, then you only have to solve for very few unknowns relative to what you have in a full-scale simulation, say. And if you have a good initial guess and you have a good algorithm for solving for these 3 tie lines or 9 tie lines or how many are tie lines, it can be very efficient. And there's a group in Denmark who have programmed up a very efficient solution method for the approximate method of characteristics. And when it works very well, very fast. But this method has some disadvantages. First of all, the assumptions that all the transitions that all the transitions occur as shocks, that has not been thoroughly verified. And they say, well, we can't really verify it, but in all of our experience so far, we see that they're pretty close to shocks. The assumption is good, even if it's not 100% accurate. Well, we don't really know how far the approximation might throw the answer off. So that's one thing that gives rise to some worries. More importantly, though, this approximate method can produce unwanted multiple solutions. This is the true solution that we want. This is the only solution that's stable. In other words, if you actually ran a physical displacement, it would by itself eventually converge to this solution because this is the one and only stable solution. But there are an infinite number of unstable solutions to the equations that are set up for this approximate method of characteristics. One in particular is a simple shock jump from O to I. That's a solution to all their equations. But it's unstable because as soon as they mix any little bit with the physical dispersion, the solution moves away from that from that particular shock. And you can have other multiple solutions. You can put a critical point anywhere, like here, and say, okay, my solution is from this tie line to that critical point to this tie line. That's a solution to all their equations. It's not the stable solution. This is the only stable solution, but there are an infinite number of other solutions that the algorithm might converge to. And unless you check somehow for the stability of that final solution, you can't guarantee that you've calculated the right solution. And just like the rigorous method of characteristics, when you get near a critical point, whether it's the true critical point or one of these false critical points, the solutions become ill-conditioned, ill-posed. So that's a big problem. Also, the way they look at it, they say, okay, we've got 4 components, so we know we have to have 3 shocks that control this solution. Well, what happens if your original oil just happened to lie on an extension of this tie line right here? Well, then you take this tie line completely out of the picture, and you only have 2 tie lines to look for. But they're looking for 3. There are only 2, but they're looking for 3, so the problem becomes ill-posed in that way. What do they find for that third tie line that they're looking for? Do they find another case where they just have 2 tie lines the same? Or do they converge to a critical point, which is the solution for any tie line? So the people who are promoting this approximate method of characteristics, they haven't worked out any of these disadvantages yet, and maybe they never can. The bottom line is it becomes kind of unreliable, because you never know for sure what kind of answer you're going to get out of there, either because of numerical instabilities in the problem, or because it finds one of these non-physical, unstable multiple solutions, or because it relies upon some assumptions that haven't been verified. You just don't know what the answer is going to be. So, so that brings us to the multi-cell, multi-contact calculations. Now, the advantages there is that, like with the slim tube simulations, it's accurate for all displacement mechanisms. It doesn't rely on any assumptions about the mechanism, and so it works for all of them. And it's much, much faster than slim tube simulations. Probably at least 2 orders of magnitude faster. Because it can be entirely automated. It doesn't rely on eyeball interpretation of the recovery versus pressure curves. Each calculated point goes much faster because you don't have to worry about the stability limits of a displacement calculation. So overall, you can find any given MMP or MME in about 1% of the time it would take you to find it with a slim tube simulator. Now, there are a couple of minor disadvantages. It requires some extrapolation. We get the right answer only if we use an infinite number of cells. But we can never use an infinite number. So this calculation method might use a finite number, 50, 100, 200. I've seen one case where I had to go up to as high as about 500. But how many ever cells you do have to use, what you want to do is you want to extrapolate those results to an infinite number of cells. And that extrapolation introduces slight uncertainties. They're usually not very significant, but there is some uncertainty there. Another disadvantage is that it's not something that you can try to program it up relatively easily, but it's probably not going to work right off the bat until you really work to make your algorithms robust, because you need high accuracy solutions as you get to the critical point, near a critical point. And if you have, if you can't converge to an accurate enough solution near the critical point, then it drives these uncertainties up. If the algorithms fail completely near the critical point, then you lose the solution entirely. So you need robust algorithms, and so it could take a considerable amount of time to program this method up and get it right. And the final disadvantage is that it's not instantaneous. We'd all like instantaneous answers, and this is fast, but it's not instantaneous. So until I can work out that little kink, it's not perfect. All right. Now, what I'm going to do next is I'm going to show you some examples of these various calculation techniques. I'm going to show you the predictions from Mmpz versus the results from slim tube experiments and simulations for both some MMPs and some MMEs. Then I'm going to show you the predictions of Mmpz versus those of a single cell method, and the method of characteristics for some solvent enrichment tests. And finally, I'll show the case of Mmpz predictions versus slim tube simulations for gas condensate minimum miscibility enrichments. And I'll say more about that when we get to that one. So the first example, comparison of Mmpz predictions with slim tube data and simulation results. Now this is a case for an Alaskan oil, and we're going to first look for the MMP for a hydrocarbon CO2 based solvent. So they've got this solvent. It's about 25% CO2, 25% methane, 25% ethane, 20% propane, and 5% butane, or something like that. The question was, well, what's the MMP of our oil, of the Alaskan oil with that solvent? And then the second question is, how much can we dilute that base solvent with methane to achieve miscibility at a certain higher pressure? And so that would be a minimum miscibility enrichment calculation. All right. So here's the first case, the minimum miscibility pressure results. Now what we have here is recovery at 1.24 volumes from a slim tube, either displacement or simulation, versus pressure. Now the red squares are the data from the physical experiments, and the purplish bluish curves, those are the results from a slim tube simulation. First with 100 cells, which gives you there's just too much dispersion there to tell what the MMP is. So then with 200 cells, it shows it gets a little bit closer, and so forth until you can finally do an extrapolation to an infinite number of cells, which gives a recovery curve that looks about like that. And so the MMP is is somewhere in this range. Now, it's just straight out of the run, Mmpz spits out one single number. It says this is the MMP, 2170 or something like that. And so we see that this predicted MMP from Mmpz, it agrees extremely well with our slim tube simulations, and it also agrees quite well with the data, which basically shows that the fluid characterization was a good characterization because the equation of state predicts the experimental MMP.
Data from the experiments, what's the multi-cells in the cell?
That was an actual slim tube experiment where they took a 40-foot tube that was filled with sand, and they filled that tube with oil, and then over a period of 8 or 10 hours they injected gas into the tube, and the tube is coiled so that it minimizes the effect of gravity. And if they run those experiments correctly, then what they measure at the result at the outlet is the volume of oil recovery versus time, and the ultimate recovery after you've injected 1.2 pore volumes gives you the one data point. So this would be the recovery of the oil at this pressure after 1.2 pore volumes. And you take you do 6 runs and you get those 6 data points. And so then you have to try to figure out usually by drawing 2 straight lines through the flat parts of the data, and the intersection would be considered the MMP.
2 days for
About 2 days for each point, yeah.
But when the extrapolation goes beyond 100% recovery, then
Well, for one thing, this is a volume recovery, and if the gas is rich enough, you can get recovery from just the pure gas. So your recovery can go above 100% if you start producing gas and you recover the condensate from the gas when you take it to surface separator conditions. So you could actually see more than 100% recovery in a physical experiment, potentially. Also, these are extrapolations to 1.2 pore volumes. It's probably actually a better idea to extrapolate recovery to 1 pore volume, because theoretically, if you have 0 dispersion, you should just reach 100% recovery at 1 pore volume. And so if you extrapolate to 1.2, you often will extrapolate a little higher than 100% from that reason. The difference is usually minor, and especially the difference in the predicted MMP. It just happens that this is an old case when I was usually extrapolating to 1.2 pore volumes, because that's where the data was calculated, was taken. And so I wanted especially to compare the simulations with the data at the 1.2 pore volume location. But that's those 2 reasons combined for producing recoveries a little bit higher than 100%. Okay.
One more question. The pressure is a fixed pressure difference,
Well,
or else the pressure at the front?
no, in the simulations, you can use basically an infinite permeability, which means you have 0 pressure drop from one end to the other. So the whole slim tube is, in the simulations, is at constant pressure. In the experiments, there's probably about a 5 to 10 psi pressure drop from one end to the other. it actually varies with time too, because when it's filled with oil, you get a larger pressure drop, and then when you have mostly gas in the tube, you get a very low pressure drop. But it's on the order of 5, 10, maybe 20 psi across the tube, negligible compared with the average pressure. So you can consider a slim tube either experimentally or simulation-wise to be at constant pressure. What was
4 minutes.
4 minutes on,
Yeah, they would
on the
take a little
tape?
break, yeah.
Oh, okay. All right. Now the extrapolation is pretty straightforward. You can plot up recovery versus 1 over the square root of the cells, and once you get in the region where extrapolation is safe, you'll always get straight lines. And so you just extrapolate these back to where they intersect at an infinite number of cells, or 0 for the inverse. And that gives you your extrapolated recoveries. And it works whether you're above or below the minimum miscibility pressure. Okay. Now, in a similar case, they took some data where they fixed the pressure at 3,100 psi, and they said, well, okay, we get miscibility with our pure base solvent, but how much methane can we add to that solvent before we lose miscibility? And so you plot up your data like this. These are all taken at the same pressure, but now with different injectants. And you see that when you get above about 40% methane in the injectant, you start to lose recovery. So this would be your minimum miscibility enrichment point. And again, the red squares are data. The thick blue curve is the extrapolated slim tube simulation results, and the single red line is the prediction made by Mmpz. And you can see that the Mmpz prediction is right in line with the slim tube predictions, and that those are in line with the data. So the equation of state is verified, and the Mmpz algorithm is verified.
So this extrapolation doesn't affect the accuracy of the data result.
Yeah, the extrapolation of the recovery curve does introduce a little bit of uncertainty, but it's a lot less uncertainty than if you tried to say, well, where's the MME on this curve with 200 cells? You can't say. You might even be tempted to say, well, it doesn't really flatten. All right. Well, let's go to the next example then. And that's the comparison of Mmpz predictions with those of single cell and approximate method of characteristics calculations. Now, you've probably heard of the PBT software, PBT Sim. They have a single cell MMP algorithm built within PBT Sim. I didn't use that program, but I used one that I programmed up myself, which is probably very similar to theirs. And then for the approximate method of characteristics calculations, I turned to a paper by Jessen, Mikkelsen, and Stenby, or Jessen, I don't know how to pronounce his name. I don't have an MOC solver myself, so I used their solution. In fact, this whole example was their problem, their published problem. So it's using published fluids. And what they've done is they've calculated minimum miscibility pressures for a range of solvent enrichments. And so I'm going to reproduce their results. And then besides doing these calculations, I'm also going to show you one slim tube verification of a key point in the results. All right? Now, here's what the single cell method predicts. It predicts a high minimum miscibility pressure regardless of solvent enrichment. Decreases a little bit, but not very much. It's very high. This would be how much pressure it would take to get a purely vaporizing gas drive miscible displacement. Here's what Jessen and Michelson and Stenby predict. They predict a rapid drop-off in miscibility pressure until they reach about 40% solvent enrichment, and then it stays flat. No more change in the MMP after that enrichment point. Well, these two curves are what Mmpz predicts for this situation. It predicts something between these two. It predicts a steady decline in the miscibility pressure with enrichment. And it doesn't matter too much how many cells you use. 100 cells, 200 cells, you get about the same answer. Beyond 200 cells, the answers change hardly at all. Well, now that you've got 3 different solutions here, which one's correct? Well, the only way to tell for sure is to run a slim tube simulation using the same model fluids as for every other case. And so the next slide shows you where the slim tube results came out. It came out right on the Mmpz prediction and far from either of these other 2 predictions. Now, why are these other 2 wrong? This is wrong because it assumes a vaporizing gas drive. That's not the case here. We've got the mixed mechanism. This one's wrong, I think, because they picked up on one of these multiple unstable solutions and stuck with it. And they didn't realize that it was an unstable solution. So they get a false answer here for this method of characteristics problem. The only reliable fast method is the Mmpz type method, the multi-cell, multi-contact method, which basically approximates a slim tube. So, let's see, what do we have next here then? Yeah.
Yeah. The slim tube extrapolation, was the experiment done?
No. No, this is just a purely model fluid, I think. I don't know, maybe they based their model on a real fluid someplace or another, but I don't know of any slim tube experimental data. They didn't publish any data. If they had data, they would have seen right away that their model results were way off. But they're blissfully unaware that their model results are so far off. So they obviously didn't have any data to compare it with.
So you did this?
Yeah, I did this the simulation of a slim tube. So basically, these are the results calculated by 2 different methods. The full slim tube simulation, which is always reliable, and the Mmpz algorithm, which so far I've never found a case where it was unreliable either. So basically, they confirm each other and disprove these 2 methods.
And these 3 different methods, actually they are demonstrating the different processes. Because if you look at the purple one, it means that this MMP is roughly independent of the solvent enrichment. And the last one is it means that after the enrichment hits a certain level, the NP is fixed. But this Mmpz illustrates that this MMP decreases when its enrichment is increases. And physically, so which one is?
Well, this one's the right one. This one is if you require that you eliminate any leading gas bank in your displacement, that you forced it to go all the way from from minimum miscibility conditions to minimum vaporizing miscibility conditions, this would be the answer. But you don't care that it's vaporizing. You don't need it to be vaporizing to produce 100% recovery. This is the pressure at which you'd get 100% recovery. This is just a plain wrong solution. This has no physical meaning to it whatsoever. You will get an immiscible displacement if you try to operate at that point. You will not get miscibility like they predict. So this is just wrong. These two are two different physical mechanisms. This one is the minimum for miscibility. This one is the minimum for vaporizing gas drive miscibility.
This solvent enrichment is based on how many components?
Well, it had quite a few. It had everything up to C7 or C8 in it, I think. The fluids are in their paper. I don't have a reference handy with me, but Curtis could always give you the reference to that paper. So they described their fluid systems. And so what they did was they went from 100% of one solvent to 100% of the other. Now, if you kept enriching it in the same way, this curve would eventually do something different. It would probably also flatten out. Certainly, at some point, you're going to reach first contact miscibility. And at that point, then well, no, it could just keep decreasing for a long ways, but until it finally, I mean, it can't go negative. You can't go to negative pressure, but it may start to level out at some point. But for this range of solvents, it didn't, and that's pretty typical for any solvents that you would actually use in a reservoir.
It means that we should have the rich gas instead of the lean gas injection.
Well, it's all a trade-off. With a rich gas, you don't need as high a pressure, but the rich gas is very expensive. Basically, it's expensive to raise the pressure in the reservoir, and it's expensive to raise the enrichment level. And so you have this trade-off, and you have to try to optimize based on economics. But if you want to get 100% recovery, you've got the choice of any point along that curve. All right? This shows you what happens with the slim tube simulations to get that one simulated slim tube point. So I simulated with 50, at least I've shown here, with 50 cells, 200 cells, and 1,000 cells, and then extrapolated to an infinite number of cells. And here I'm doing it to a recovery of 1 pore volume. So the extrapolated result, where it just hits 100%, that would be your slim tube predicted MMP. And this red line is where MMPZ places it straight off. So you can see that there's excellent agreement between the two. This is where Jessen puts the MMP. Well, 60% recovery in my book is not miscible. So it's clearly a false solution. All right? Now, this is the data set that calculated that entire curve of MMPZ results. It's very simple and straightforward. You input your characterization in a table like this for the critical parameters, and you input your binary interaction parameters in a table like that. All right. You define the fluids involved. You mix up an oil. You mix up a lean gas. You mix up a rich gas. Then you set your temperature and feed composition. So this is the temperature. And then you mix your feed composition, and you take 1 tank of this oil. And then you calculate 100 and 200 cell MMPs for varying injectant mixtures. So to mix up the injectant, you mix so many tanks of the rich and make it up to 100 total moles of the lean. And then you do an MMP with 100 cells, and you do an MMP of 200 cells, and you do this for a variety of injectants from 0% rich to 100% rich, and you're done. So that's the entire data set to calculate that entire set of curves. If you wanted to do the slim tube simulations, you would have to make roughly on the order of 20 or 25 individual slim tube simulations. So you're talking about 20 or 25 data sets. Each one, the data set that is required by a reservoir simulator, and you know how complicated those can be. It'd be a nightmare to put that together. And this is just one simple 2-page data set, and you get the whole suite of results. Okay? Now, example 3, comparison of Mmpz predictions with those of slim tube simulations for a condensate system. Now, the guys who do the method of characteristics, they can't even handle a condensate system at all. And most people haven't even thought about, well, what's the miscibility of minimum miscibility conditions for displacing a condensate by gas. Most people think, well, you just have to keep it above the dew point. That's the requirement. But that's not exactly the case, because you can let the pressure in the gas condensate reservoir drop below the dew point, and as long as you can miscibly displace the condensate that falls out, you can still end up with 100% recovery. But to calculate the MMP for a condensate system turns out to be much more difficult than for an oil, because the path takes a much more convoluted path through the composition space. And with slim tube simulations, it takes an enormous number of cells. And the method of characteristics, that they haven't been able to get that to work at all. But I'll show you how Mmpz can do it. So what I've got here is another set of published fluids by Lars Heyer. And what he was looking for was the minimum miscibility enrichment between two solvents at a fixed pressure of 5,000 psi. And what he saw was enormous difficulty with the slim tube simulations, because they kept changing a lot until he got to a very high number of cells. So here's just an example. 50 cells down here shows almost no change in recovery. It's basically just immiscible the whole way. Now you start to get an increase in recovery if you go to 250 cells, and more if you go to 500, and more at 1,000. And the best guess for the extrapolation to an infinite number of cells is this curve here. And you barely have enough cells to extrapolate to infinity. But I think it can quite just be done with that number of points. Well, Mmpz gives you the answer right off the bat to essentially the same value that you get from this extrapolated slim tube simulation. All right? And Mmpz does it with very little dependence on the number of cells. This is the minimum miscibility enrichment predicted by Mmpz as a function of cell number. And it goes down a little bit and comes back up a little bit, but it's essentially independent of the number of cells, even though the slim tube displacement itself is highly dependent. And we'll see what kind of dependence you get from that. This is just above miscibility conditions, and this is with a 1,000 cell slim tube simulation. And what you're looking at here is this shaded area is the oil saturation at 3 different snapshots after 0.2 pore volumes injected, and after 0.6, and at 1. And you can see that it takes something like 300 or 400 or 500 cells of injection before the mechanism develops, so you get a fully developed oil bank. Until that 300 or 400 cells of contacting, you haven't captured the right nature of the displacement. Meanwhile, here are the densities of oil and gas, also at these 3 snapshots. You see that as you go farther downstream, the front region, the densities become closer and closer, but they never quite reach, even though this is above the minimum miscibility enrichment level. But anytime it takes this long, this many cells to develop the correct miscible front, you're going to have to use a lot of cells to do your slim tube simulations. All right. Now this is right at the, or maybe just slightly below the Mmpz. It's either at or slightly below, but you can see that now the bank has not even developed by 1,000 cells injected. So you see the densities are approaching a little bit, but they don't have that sharp peak like they did at the higher enrichment level, and the oil bank is not nearly as well developed. So the slim tube simulator is going to predict considerably less than 100% recovery in this case, even though it is slightly above the minimum miscibility enrichment. Okay. This is the data set for running the entire suite of results through Mmpz here. Okay. Next slide. And it's very similar to the one we had before. Basically, calculate the minimum miscibility enrichment with 4 different numbers of cells, and those were the 4 on that one plot, and that gives us our answer. Okay. Now, let's see. I'm going to try to quickly explain how this works. Basically, as miscibility is approached as the displacement distance goes to infinity, and the number of contacts goes to infinity. So what we want to do is we want to monitor the distance from miscibility as a function of distance and contacts. And if we can extrapolate that distance from miscibility out to an infinite number of contacts, then we can see whether we actually reach miscibility or not. If that distance goes to 0, we're miscible. If it stays finite, we're immiscible. And then the program adjusts the pressure or the enrichment level until this extrapolation just hits a 0 distance from miscibility, and that would be your minimum miscibility condition. And so basically, this would be one measure of miscibility that you could use. The distance between the densities of the equilibrium oil and gas at their closest approach. So you see that distance is decreasing with distance, and if you can extrapolate that out to an infinite distance, you can see whether you've got miscibility or not. Okay. Another way of doing it would be to look at the tie line lengths, and this is kind of This is the surface followed by the composition path. That's what I've tried to draw here. And this is for a finite number of cells, so it's still a curved surface. It doesn't yet form two surfaces that interact in a discontinuous way. But if you measure the length of these tie lines and you go to higher enrichment levels, okay, then that tie line goes shorter and shorter as you go to more cells injected. This is, the first was at 1 cell. Okay, the second one is at 25 cells downstream, and the third one is at 100 cells. And so you see that that tie line distance gets shorter and shorter the closer you get to the true solution. So that's another thing that you could measure or monitor as a function of distance. All right? And if you do that, in this case, the minimum tie line length, and you plot that up as 1 over the square root of the cell number, for example, and you do that for varying pressures, you see that at the low pressures, they extrapolate to a finite value at an infinite number of cells. At high pressures, they either actually go to 0, or else they extrapolate to something below 0. So those would be miscible pressures. These would be immiscible pressures. And the Mmpz would be the pressure at which it just extrapolates to 0. So it would be somewhere between this green and blue curve. So somewhere between 345 and 350 atmospheres. And you can go to a higher number of cells and refine this area of the plot, okay? And you see more clearly that, yes, it's somewhere between 345 and 350. And so the program does that all automatically. It's all automated. But in order to get these nice, smooth, extrapolatable curves, it has to be very robust near these critical points, because you're getting very close to a critical point with these calculations here. So if you didn't have robustness, you might, the whole algorithm might fall apart. So that's really the only trick to the program, is being able to calculate these curves accurately. All right? Now, besides the MMP and MME calculations, which can be done regardless of mechanism once again, whether they be vaporizing, condensing, or mixed. Mmpz is, I've also built in many other features. It can use any of these 4 equations of state. You can also do flash calculations, saturation pressure calculations. You can mix fluids and store them in a very flexible way. It can be used to identify multi-phase conditions. In some cases, when you inject a particular gas into a particular oil at a certain temperature, especially if the temperature is on the low side, it can actually enter a 3-phase region in phase space. And that's okay as far as physically. The mechanism in the reservoir doesn't care whether it goes through a 3-phase region or not. But if you have an EOS model that predicts a 3-phase region, and you try to run reservoir simulations with that model, the simulator is going to just crater. It will not be able to get through those 3-phase calculations, because it's only calculating a 2-phase solution, and it'll oscillate between 2 different choices until the time step goes to 0 and the simulator gives up. So you really want to avoid 3-phase models that predict 3-phase, and Mmpz is a real good way of quickly identifying whether you're going to run into that problem, because you can ask it to check for each calculation whether it hits a multi-phase condition. And it's flexible and powerful, but still pretty easy to use. Tiny little data sets are all you need. And it's the first module of a complete PVT package that I'm working on. I've actually added quite a few more features beyond the flash and saturation pressures already. You can do any of the normal experiments, CVEs, DLEs, constant composition expansions, swelling experiments, multi-contact experiments, vaporizing type multi-contact vaporization experiments. So you can do all of those things now too. And so eventually, once you get out into the world of industry, keep this program in mind because it'll be really useful for doing your phase behavior calculations. And to give you an idea of that, next we're going to actually put together a simple data set and run some calculations so you see what it's like to work with a program like this. Okay. Now, has everybody downloaded the file yet, or is it still to be?
It's there for download.
Okay.
You want to explain
Why don't I let Coda instruct you on how to snag the files you'll need.
You all using student accounts or any other way? You have to use a FTP program. The FTP server or IP address that you have to specify is 129.24.
It's not designed for any particular piece of software. And so we're going to first manipulate it into the form that Mmpz needs. And so what I want you to do is I want you to make a copy of this data set so that you don't screw up the original. All right? So now I've got a workbook 1 with this data set. And so the first thing we want to do here is up at the top for the title, we want to tell the program that this is a title. So we'll go ahead and add quotes around it.
Okay, you want.
And now a peculiarity of Excel is that if you want to put quotes around, single quotes around something that's in a cell, you have to actually put 2 of those at the beginning. Or else it loses the first one. See, it always strips off the first one that you put on there. So now we've got a case where we have quotes around there. Now we have to add a keyword. So we inject a cell, we shift these to the right, and we just say title. Okay? So now we have title, Jessen Michelson Stenby fluid system.
We all have the data set?
Okay. All right. Now the next step. This looks like our fluid characterization, and it's almost in the form that we need it. But we need a characterization keyword.
So, Aaron, can you wait just 1 second? We've got to. Does everybody have the Excel data sheet up?
No.
Okay, so we have to do that first.
You don't know how to do. Insert a title keyword, and then put quotes around the title up there. All right. Does everybody have that? Okay, then the next thing is you want to insert a characterization keyword. You can go ahead and give this characterization a name, and let's just call it JMS. Okay? So it will look something like that. And then the EOS, that's actually a keyword, EOS SRK, that's fine just as is. And this table is can be read directly by Mmpz except for this eccentric factor. We need to change that cell just AF for eccentric factor. And these binaries, Mmpz can read that binary table just as is. Now here we've got, we have a little bit of a, we have to do a little bit of editing. We want to get rid of this line, the fluid compositions, because that's, that we don't need. And now the component keyword, that's also not recognized. So let's change that to mix. All right. Now let's. Oops. Okay, let's copy this range of cells and duplicate it 3 times here. Okay, so got 3. Now, the first case, we can blank out those 2 columns. So now we have mixed oil, and then it gives the compositions there. And in the second case, we can kill the oil column and blank out the rich gas column. And then we don't need these extra components kicking around, so we can kill those. And in the third case, we can kill the first 2 columns and just leave the rich gas column there. Kill the extra unknowns. So this is just one of many ways that that Mmpz can read compositions. The mix is the primary keyword, and now we've named these fluids. Oh, one more thing. You have to take out the space between lean and gas, and also the space between rich and gas. All right? So we're defining 3 fluids: oil, lean gas, and rich gas by name. And we're giving the compositions in this form here. Now, we can set the temperature of our PBT cell. So we can just remove the word reservoir. Also for pressure, remove the word reservoir. And out here, actually that's fine. Even the tildes are okay. They'll be ignored. Now, just for the heck of it, let's mix up our feed composition. This is what actually gets fed to the PBT cell. And we'll just feed all of the oil. All right? And then let's do a saturation pressure calculation. All right? And if you get the data set to that point, then you can save it as a text file. Make sure you save it as a text file and not an Excel file. So I'm going to go ahead and do that. Save this as, I'm going to call it jms.tab, and save it as a tab delimited text file. All right, just the first sheet there. Now, I can go ahead and run Mmpz, assuming I don't have to close it up with that. Let's see. I need to close it in Excel also. Save. Oops. I did something wrong here. Oh, okay. That's the. What I told you originally, we want to change this title line to just car JMS so that there's not an extra tab between. This is kind of screwing it up the way it's looking for a title string if you have two tabs. So just have one, just tab to the second one. And then the tildes that were in front of the temperature and pressure, you have to remove those tilde characters. But then after you save this as a text file, it should run in Mmpz. And you can play around with that between